Yep.
Perfect. Excellent. All right. Hi, everybody. Again, I'm Niklas Bohn from NASA JPL in Pasadena. So good morning or good evening, wherever you are. So I'll be presenting on the EMIT mission today. So thanks again for inviting me to this seminar. Initially, the idea was to talk about SPG. But as many of you may know, SPG is kind of in a kind of on hold status right now because of the uncertainty in the budget for the next year. So I just switched over to EMIT because EMIT has been doing some contributions to cryosphere science in the past, even though it's not the prime mission focus, or it was not the prime mission focus. But there's a lot going on, and I'll just give an overview today about activities where the imaging spectroscopy mission is involved in terms of snowmelt prediction, supporting decision making for water resource management. Yeah, thanks of course again to all of my co-authors here. It's just a joint effort of different people. Big thanks in the very beginning here to Jeff Dozier, who was an essential part of EMIT, of SPG, of all the kind of past decades for hyperspectral remote sensing. And this talk is again, as many of my talks, dedicated to him. He had an EMIT Roses project going on last year, which might continue in some way, but this is also including some of his initial results from last year. So let's go into the introduction here. So what is the motivation for our imaging spectroscopy or hyperspectral remote sensing for snow? So we basically are interested in the snow albedo darkening and the LLP radiated forcing. So any kind of increased absorption due to any kind of light absorbing particles on the surface. So this is really the main motivation, and also provides a connection to the EMIT mission, which is, and I get to this in a second, primarily looking at dust source regions on the Earth. So these are just some examples from recent studies in the past decade for looking at dust deposition on mountainous snow. So for example, in the Russian Caucasus, but also in the Himalayas. And as you can see, if all these dust particles deposit on the snow, it gets darker in terms of it turns into these all like bright orange or dark brown colors, absorbing more light, increasing the absorption and the radiative forcing. And how this manifests in the spectra, in the optical solar spectrum, you can see these examples in the top right here, where you see all this kind of increased absorption in the shortest wavelength, where actually the sun's energy is highest. So that explains why you actually get all these kind of impacts on the radiation balance. Besides the actual quantification and detection of these particles, it's also important to make the connection to water resources risks. And there are some examples from Afghanistan and India where you can actually see, and this is very interesting, on the right here, you see the retreat in glacial length, and correlated to that, the development in air temperature, but also the kind of time series of deposited carbon concentration and dust on the snow surface. And you can see that there's actually a higher or more significant correlation of glacial retreat to these particle depositions than to air temperature. So it's actually highlighting the importance of getting an overview and an insight into these depositions of these particles, and how that affects actually not only the albedo of the snow, but also how this kind of trickles down to the water resources supply for especially arid regions and close to mountain regions. So what is EMIT? Not all of you might know what EMIT actually is. So it's an imaging spectrometer installed on the International Space Station. Launch was in 2022, July 2022, and you can see this kind of nice image here. So this kind of block here, that's EMIT installed on the ISS. This is EMIT in the clean room before launch. And the way it works is basically just like a camera. So it scans the surface in continuous rows. But except like contrast to a kind of classic camera, it has hundreds of different channels within the solar spectrum, the optical spectrum between 400 and 2500 nanometers. So it actually gives us these kind of spectra for each single pixel in this kind of image cube or flight line. And we can turn this into a three-dimensional image cube, as you can see here in this plot. And then having these radiance measurements, so it measures the reflected sunlight from the surface, having these radiance cubes, so photons, photon counts, we can go through the atmospheric correction step to get surface reflectance and then produce any kind of subsequent level 3 product maps like minerals or snow parameters. So the prime mission focus of EMIT was to look at desert regions of the Earth, to map the mineralogy of these regions, to get a better input to Earth system models, improved input, so that modelers can actually better model the dust transport and the dust source and things on the Earth. So it's all this kind of connection between particle emission and transport, deposition, radiative forcing, and how this is all connected also with atmospheric patterns. For example, like these dust storms that happen every now and then coming from North Africa, and then also affecting the weather situation in Europe, for example. So the obvious connection to snow, of course, is the deposition on snow surfaces. So when all this dust gets transported, and this is what I showed on the first slide, it travels through the atmosphere and gets deposited on snow surfaces. And this is an example from Colorado, and you can see all these kind of darker surfaces here, which are basically just caused by deposition of these particles. So this is really like the connection between EMIT's prime mission, which was to look at these mineral regions and deserts, and then the connection to mountains. And as you know, many of the deserts on Earth are very like in close proximity to mountains. So there's a very obvious connection between these two surface types. So EMIT actually observes the Earth system. This is just an overview about all the different ecosystems. So we have aquatics, we have terrestrial ecosystems, we have solid Earth geology and soils, so the mineralogy. But an essential part, of course, is the hydrology. So snow and ice physics, seasonal snow, mountain snow. For EMIT, not really high latitude snow because EMIT is on the ISS, so it's kind of restricted to mid to low latitude. So we can only take acquisitions for like up to 55 degrees north and south. So that's the limitation we have. So we don't have any images from Alaska, for example, or Canada or Greenland. But this is what we get. So as again, we get these spectra for each pixel, and then we get these image cubes, three-dimensional. And so the swath width for EMIT is 75 kilometers, and the pixel size is 60 meters. So the objective of this talk, but also of the EMIT snow and ice focus is really like to assess the role of EMIT in improving snowmelt prediction and supporting decision making for water resource management. This is kind of Jeff Dozier's legacy because he won the project for the EMIT Computed Science team 2 years ago. His project title was slightly different. So he was talking about the role of EMIT and thermal infrared remote sensing in addressing the decadal surveys, most important objectives for snow and the water cycle. So his idea was really connected to SPG and CHIME, the hopefully upcoming global imaging spectroscopy missions. So he was really looking at the decadal survey, where he was a co-author, and how EMIT and also the thermal mission EcoStress, which is also on the ISS, can actually serve as precursor missions to those global missions. Just a quick go back to the decadal survey, especially for the snow and ice and hydrology focus areas. So what really is in the decadal is that we should quantify the snow and glacial albedo and surface temperature for subpixel snow at weekly intervals. And they also give some accuracy estimates here, so we should be able to get these parameters of for an accuracy of up to like maximum 10% error in the absorption. Main parameters of interest here are the snow and ice coverage fraction, surface reflections, of course, and then grain size used to calculate the albedo. And this is what EMIT can actually deliver. So Jeff was really like focusing on these objectives here and was trying to look at EMIT. How can EMIT actually serve as a precursor? What can we learn from EMIT in terms of uncertainty budget and parameter retrievals? So these are some example products here. This is an EMIT scene from the Alps. This is the Aosta Valley. Italy, and you can see that from the actual surface reflectance, you can go through some unmixing procedures, for example, to fractional cover, to grain size, and finally to broadband albedo. So this is the most the parameter of most interest following the decadal survey. As I mentioned before, so we're still hoping to get this new era of spaceborne imaging spectroscopy out. We have challenging times right now with SPG. CHIME is going on, led by ESA in Europe. And we still have hope to get this in space at some point, which has a few main differences to the EMIT mission. So spectral range, spectral bands is basically the same. Also, SNR is in the kind of same ballpark, but the differences would be that we would have a smaller ground sampling distance. So would have pixel sizes of like roughly 30 meters instead of 60. And also, EMIT is not revisiting every location on Earth in a specific frequency. So it's on the ISS, so it has a very infrequent observation cycle. So it could happen that EMIT covers the same spot twice in a week. It could also happen that EMIT covers the same spot only twice in like 5 months or so. So with the idea for time at SPG, we would actually get to this kind of biweekly or even combining both missions, 8 days revisit time for every single place on Earth. So this is really the difference, and we're working hard to get this going. But for now, I'll focus on what EMIT has accomplished so far or has contributed to the cryospheric science, and all the activities that have been going on that will be going on in the future. First of all, looking at an interesting issue here that Jeff was tackling last year, which is I'm not sure if it's commonly known as the hooking issue, but he was referring to it as the hooking issue, which is a interesting behavior in our surface reflectance for snow, where we can see as this kind of downward hook in the shortest wavelength. So this black spectrum here is a retrieved image spectrum for snow, so surface reflectance, and you can see that the reflectance goes down in the blue wavelengths here around 500 nanometers and below, even though this is basically a clean snow spectrum. So you usually would only expect this when having all these particles on the snow absorbing the light. But in this case, it's kind of an artificial absorption that is not really present. So Jeff was doing some investigation here, how you could actually improve snow surface parameter retrievals by, for example, bypassing these wavelengths and not looking into them and not using them for modeling. Because what would happen is if you include those, this is shown here in this kind of small table, you would actually highly overestimate the dust concentration because your algorithm would think there's high absorption going on, so you actually have a lot of dust on the surface. If you don't include these wavelengths, you actually get to a way lower dust retrieval, which makes more sense. More importantly, if you compare this to broadband albedo retrievals, without the hook, and also with the hook, you can actually see that the albedo is underestimated when including this shortest part of the spectrum, and also the absorption is overestimated. So you get actually a higher absorption error when including this artificial hook, which makes sense, and you decrease the absorption error significantly by not including these wavelengths. So this is one option to go forward. Simply just excluding these wavelengths in our measurements. Another option would be to determine the causes of this hooking issue and somehow trying to get rid of it. So what we've done, for example, this summer, we flew with our Everest airborne spectrometer, which one of them, we have a few here at JPL. So this is already Everest 3. We also have Everest Classic, Everest Next Gen, and Everest 5. So you may know these from some previous campaigns. So Everest Next Gen, for example, was deployed for SnowX, was deployed for ARC-6, so has been looking at snow targets in the past. So what we did is just we flew over some spots in the Sierra Nevada here in California, looking at some lakes and snow-covered lakes and glaciers. And we flew at different altitudes just to test a hypothesis that this hooking issue might be a function of the path length of upwelling photons, basically because we're kind of wrongly estimating the upward transmittance in our atmospheric correction scheme. This is just one example what we could do. So we could fly airborne instruments at different altitudes, which is of course not possible with our spaceborne instrument, to get some reference data, some validation data. This is also this hooking issue is also detailed in a recent publication from Ned Baer, Brief Communication in the Cryosphere, where we actually looked at different causes of this hooking issue. Another option is, of course, to do in situ validation. So we went out here to Lake Mary, which is one of the mammoth lakes in the Sierras this spring, did some ASD and SVC measurements on the snow-covered lake, coincident with an emit overpass, which you can see down here. And the interesting thing is we observed the same behavior on this flat snow surface on the lake. You can see the emit retrieved reflectance in red here in these plots, and you clearly see this downward artificial hook, even though the snow surface was clean. So we were on site, and we confirmed that there were no significant amounts of particles on the surface. And the field data don't show this behavior. So this is a very nice proof that the hooking is some kind of artificial, or basically it's either a radiometric instrument calibration issue, nonlinearity or something, or it could also be that we're still not including all the kind of physical effects of the surrounding terrain in our atmospheric correction scheme. So moving forward, I'll briefly want to highlight on a ROSIS project that's going on right now, where I especially want to mention the contributions from Brad Wilder. He's a postdoc here at JPL, and he's been doing a lot of great work in this project. So what I'm showing here in the following like 5 slides or so is basically just input from Brent. He did a great job in this project, producing figures, working on code implementation and the project. So this project is called Melt Metrics, and it's basically supposed to, we called it like modernized regional to global scale snowpack dynamics monitoring. But the idea really is to utilize remote sensing observations from hyperspectral instruments, beginning with airborne average data up to emit data, to improve albedo estimates as input for energy balance snowmap models like ice snowball, for example. As the next step, this should serve as an improved input to land surface hydrology models like WRF Hydro. So we want to focus on this whole like pipeline from the data input through snowmelt modeling to the hydrology models, how we can actually improve this by using hyperspectral data like IMIT. Our study site is the Kings Canyon watershed. So we are collaborating with the Kings River Water Association in this project. And so we're looking at this watershed, and especially at the reservoir at the Pine Flat Dam. So this is just the kind of use case where we actually want to create a pipeline that can forecast snow water equivalent and runoff at Pine Flat Dam, especially leveraging these improved daily albedo maps by using the input from emit data. And the overarching goal here is to like be under 2.5 to 3% full albedo error to ensure that it meets the very tight temporal requirements for water managers and decision making. You can see this in this plot on the right. So actually the error should not exceed 2 days in fraction peak of snow water equivalent. So this is really important to highlight here during the melt season. So what we've achieved so far, and again, thanks a lot to Brent, was looking at how we can actually improve the albedo coming from emit. And this is really tightly connected to what I was explaining before, that we're looking at how this surrounding topography and terrain influence emit data. And we're just looking at different characteristics of the surrounding surface. So reflection from neighboring pixels, slope in view shed, spherical albedo. And what we can actually do is by comparing this to our field data, which are displayed in gray in this plot here, that we can actually improve our reflectance estimate from emit by solving for all these kind of background contributions, which is the black spectrum here compared to the orange, which is the initial retrieval from emit. This also gives us a better estimate of broadband albedo by solving for optimal terrain we are finding more accurate spectra here, and we can also leverage this framework to get a posterior error distribution for our parameter of interest. The next step would be a kind of data fusion approach where we just take in data from different instruments, because as I mentioned before, image coverage is not as great as it should be for getting weekly or even sub-weekly estimates. So we combine this with HLS and VIRS. We use some data fusion method developed here at JPL by Maggie Johnson to get to direct and diffuse albedos as a kind of like fused data product from these input sensors. Other activities that have been going on in the past are also related to fused snow albedo products. So we did some kind of collaboration with Carl Ritger and Ross Polomaki from Colorado, and where we also looked at how we can actually improve fused data products by using emit-derived snow albedo. So what we did, it was like a few months ago, was looking at emit-derived snow fractional cover and grain size products. We compared MEMSCAG output to Spires, and also how we can combine this potentially with Landsat and Modus products. So that was an activity that has been going on for a few months now. And these are just some initial results from the emit-derived products here, where you can see reflectance, fractional cover, grain size, and also the associated uncertainty. Ultimately, another idea we started a few months ago was with colleagues from Caltech, where we used emit-derived snow albedo to inform snow depth and thermodynamics modeling and climate models. This is with Andy Charbonneau and Tapio Schneider from the Klima group at Caltech, where we also basically did the same. So we went from reflectance to spectral albedo to broadband albedo, and started to look into how it's actually possible to improve input to climate models and the parameterization of these models by using emit-derived parameters. One issue that came up here again, which also kind of highlights the importance of missions like SPG, is that the temporal coverage of emit is just too sparse. So it's really hard to use emit data as a kind of frequent input to these models, because we just, in some cases, have measurements every like 2 or 3 months, which is, of course, not enough to get any kind of useful information out of it. Finally, we can also look at the data fusion between our instrument and thermal infrared data, which is also critical to quantify snowpack and water supplies. And it comes back to Jeff's initial idea to combine emit and ecostress. So this is just an example, again, from the Ulster Valley, where you can look at emit snow cover, broadband albedo, but also ecostress surface temperature. And you can see that these are nicely aligned. It makes sense from an elevation and snow cover standpoint. And it makes total sense because both instruments are installed on the ISS, and they actually observe the same spot at the same time. So it should be way more like used in the future that these two instruments actually are available and deliver data from like both space and time coincident points on the Earth. So as a summary and outlook, so again, beyond its prime mission, EMIT provides an excellent coverage still of mid-latitude mountains snow cover. We can connect this to the mineral maps coming from the prime mission, and we can get a better understanding of this dust deposition on snow. We're working hard towards more comprehensive and surface-specific forward model parameterization in our processing pipelines to get a better estimate of snow surface reflectance, but also snow albedo, so that we can actually support development of snow and hydrology strategies for the next decade. And snow and ice science application is really now starting to be informed by latest results from EMIT. So there's a great potential from EMIT, but also from the fused products from EMIT, but ecostress, but also other sensors like EMIT, Modus, Landsat, so that we can actually combine all the different information and resolution to get a better fused parameter product here. With that, I'd like to thank everybody for listening, and I'm happy to take any questions.
Thank you, Nicholas. That was fantastic. We'll open the floor to any questions. You're free to write them in the chat or just turn on your mic and ask. I can go first then. I have a question, I guess, in the world where SPG is coming, do you know about any communication with ESA and NASA to make the instruments complementary to each other? Or was there any sort of orbital synergies they were thinking about so there wasn't overlapping as they are similar sensors?
Yeah, we actually had a lot of conversation going on in this context for it's been going on for a few years. We had different working groups, we had meetings. Colleagues visited us here, and we also went to ESA in the Netherlands, talking about synergies, and we had working groups looking at the reflectance retrieval so that we kind of make sure that we use the same kind of almost the same kind of processing pipeline. So the plan really was, and Jeff Dozer was really heavily involved in that. The plan really was and still is, hopefully, to get both sensors in space and finally have 8 days for visit time for every spot on Earth. So that was really the plan, like a very close collaboration with ESA colleagues. Um, and so yeah, that has been going on quite heavily.
Awesome. Thank you. And it's amazing to see you continue to highlight Jeff's work and his importance towards these topics and stuff. I
Yeah,
really.
it just wouldn't have been possible without him. So he was
Mhm.
just a so important contributor to all this kind of hyperspectral and also other areas in snow science that it's just essential to highlight his work and also because he still had so many plans for the future. He was just like half a year into his project last November. So it's just yeah.
Yeah. And I know too that I guess that question came from I know there's conversations about like Roselle and Nisar and how they could possibly complement each other. So it's really cool to see North American and European cooperation of, not to overlap each other.
Yeah, absolutely. And I think I didn't mention it, but I put it on my slide somewhere that NISA is really important for us because it could actually give us also better information about the surface, like digital elevation models and topography. So this is really important to combine this with our modeling. So absolutely.
Cool. Any other questions?
I had a question on the incorporating emit with the climate model from the Tapio Schneider's group. I was curious what would be needed from emit. I know you talked about temporal resolution, but are there any other tricks that you all can do or that you all talked about in order to incorporate the instrument with climate models?
Yeah, so the obvious trick, of course, is to just use data fusion with other sensors, to just use emit high SNR and high spectral resolution to improve fused products from instruments like MODIS, Landsat, or so, which have a lower spectral resolution. But another idea that we haven't really explored yet, was looking at like the same image at different spots in the image and use some kind of machine learning uh, extrapolation methods to get basically kind of artificial temporal information from the same image, which is of course not the best way to go, but it might have some potential to get at least more like let's say denser uh, data points. Because as I said before, it's really a challenge with emit in terms of the temporal coverage. So that's just because of the ISS orbit. So that's how it goes. And by using just emit data without any complementary other like sensor data sets, it is almost impossible to get a useful input to these models or like any kind of products on a like useful time scale because the steps between data acquisitions are so infrequent and too big at many times.
Cool, thanks.
Cool. We will move on there. Thanks again, Nicholas. And now we are having a presentation from Dr. Devon Dunmire. Devon is, as of the last day today, a postdoc at KU Leuven in Belgium, but then coming back over to the United States. She has expertise in a large range of cryospheric topics, ice sheets, and also snow hydrology. So Devon's talk is titled today, The Importance of Dynamic Observation Errors in Snow Data Assimilation. And take it away, Devon.
Yeah, thanks, Jack. Let me just share my screen quickly. Okay. Okay, can everyone see the slides on my screen?
Looks
Yeah.
good.
Great. Okay. Yeah, thank you, Jack, and thanks to Jack and Kate for organizing this and inviting me to speak today. I'm really excited. As Jack mentioned, I just recently finished up a 2-year postdoc at KU Leuven in Belgium, and so I'm excited to share some of the work that my group has been doing here in Belgium and that I've been doing over the last few years. So obviously, we're all here. We know that snow is an incredibly important natural resource, and that there's still really critical challenges for estimating snow depth in mountainous complex terrain. And snow in the mountains can be quantified in a variety of ways, including with in situ measurement stations, airborne LiDAR surveys, and satellite observations. And so specifically in my research group at KU Leuven, we work with snow depth retrievals from the Sentinel-1 satellite. Many of you are probably familiar with this product, but for those of you who are not, I'm going to speak a little bit about how this works. So Sentinel-1 transmits a signal, and over land, this signal typically has vertical polarization, and the instrument then measures the radiation that is scattered back to the receiver, both with vertical polarization and horizontal. And we use the terminology VV for vertically transmitted, vertically received, and VH for vertically transmitted, horizontally received. And the Sentinel-1 signal can penetrate ice and snow, and in anisotropic snow, volume scattering occurs, which changes the polarization of the electromagnetic radiation from vertical to horizontal. And so this means that there's a relative increase in the backscattered signal that's returned back to the satellite with horizontal polarization. And as the snowpack builds, more volume scattering occurs, and we get an even greater return of this VH signal relative to VV. So here on the right, I show an example of this. We have in situ snow depth indicated with the black dots, and the red dots show the difference in the Sentinel-1 VH and VV signals for this specific site, and this is referred to as the cross-polarization ratio. So you can see that as the snow depth increases, so does this cross-polarization ratio, and that is an indication of this increased volume scattering as the snowpack builds. And this is the concept. This concept is the basis for an algorithm that was developed by Levens et al., which utilizes changes in this cross-polarization ratio and relates these changes to changes in the snow depth. And this algorithm has been used to estimate snow depth across the European Alps and other mountain areas in the Northern Hemisphere. So here we see a video of these Sentinel-1 snow depth retrievals over the Alps, and they've been shown to correlate reasonably well with in situ snow depth measurement sites. However, this method has some known issues in areas of shallow snow when there's melt or in areas of dense forest cover. And so there's been a lot of additional work recently that has been done to evaluate this product in different regions of the world and different mountain ranges, or that has assimilated this product into snow models. And so for much of the rest of this talk, I'm going to be talking about data assimilation and what exactly do I mean by this. In data assimilation, we essentially have two ingredients. The first is some physical model that represents a system, and the second is some sort of observational information. And in data assimilation, we update the model using this observational information with the goal of achieving a physically consistent representation that is closer to reality. And so in the work that has been done here in my research group at KU Leuven, we utilize the NOAA MP land surface model. This land surface model has a 3-layer snow model component, and we force the model with downscaled ERA 5 output. We often work on very large domains, so for example, the entire European Alps. And so we use a 1-kilometer horizontal spatial resolution for these large domains. And then the observations that we assimilate are from the Sentinel-1 snow depth retrieval product. So I'll briefly share some of the work that we've done over the Po River Basin, which is outlined here in Italy. In this product, we assimilated the Sentinel-1 snow depth retrievals and also backscatter for soil moisture data assimilation. And we also modeled irrigation to get a complete digital representation of the water balance within the Po River Basin. We validated the snow data assimilation component using a network of in situ snow measurement sites shown here with these blue dots, and also some manual SWE measurement stations or sites within the Val d'Aosta, indicated by the red X's here. And we also evaluated modeled stream flow by comparing with a number of gauge measurements within the Po River Basin. So we found that the assimilation of the Sentinel-1 snow depth retrievals with this data assimilation, we were able to improve modeled SWE. So here you see a comparison of measured SWE along the x-axis and SWE from the NOMP land surface model on the y-axis. The open loop is the model run without data assimilation, and you can see that with data assimilation here on the right, we improve the SWE air and bias compared to the model-only simulation. And the DA also further led to improved spring streamflow representation at a majority of the validation sites. So the figure here is showing a change in the relative spring streamflow air from this data assimilation. However, we also found that the data assimilation led typically to increased deep snowpacks at higher elevation, and this further contributed to a delayed snow meltout, which then degraded the stream flow farther along in the summer. So we had improved spring stream flow, but degraded summer stream flow. We did not assimilate the Sentinel-1 snow depth retrievers during the melt season because it has been shown that the Sentinel-1 satellite is obviously not suitable for snow depth retrieval during periods of wet snow. And so this problem of deteriorating summer stream flow could potentially be improved by assimilating some more suitable observations later on in the melt season. And so in the next part of my talk, I want to focus on two main advancements that I have made within this work. And the first is the use of machine learning to enhance these Sentinel-1 snow depth retrievals. And the second is with the data assimilation. So here we demonstrate the importance of considering dynamic observation errors. And this gets more at the actual title of my presentation. And I'll come back to this a bit more in a few minutes. But first, I'd like to explain these machine learning snow depth retrievals. So in this work, we combine Sentinel-1 satellite imagery with snow cover observations, topographical information such as elevation, slope, aspect, and topographical position index, or TPI, which is essentially an indication of whether the terrain is relatively low or high compared to its surroundings. We also combine with other land cover information, so forest cover, fraction, and snow class, which is based on the terrain's climatology. And we combine these features within a machine learning framework. Here I used the XGBoost model, and this is done to estimate snow depth in the European Alps at a high spatiotemporal resolution. So this method provides snow depth estimates at 100 meters for each Sentinel-1 overpass of the European Alps. We have trained and tested the model with in situ snow depth measurement stations from across the Alps, and also with some spatial snow depth surveys from the area within this black box here, which is the area near Davos, Switzerland. And I'll briefly share some of the model results compared with one of these airborne snow surveys. So the survey here that is shown in this smaller box was taken using airborne photogrammetry on March 16th, 2017. The dots that you see within this plot are the in situ measurement sites, and they're colored according to the snow depth that was measured on this day at that site. And now I show the 100-meter snow depth predicted by the machine learning product and also by the previous Sentinel-1 snow depth retrieval algorithm, both at 1 kilometer and also at 100 meters. While all of the products overpredict snow depth for this scene, we can see that with the machine learning, we have the lowest error, and also at this 100-meter resolution, it's capable of capturing some of the finer scale topography-driven variability in the snow depth. So you can see here the impact of some local ridges and troughs on the predicted snow depth. And with these machine learning enhanced snow depth retrievals, I have assimilated them into the NOAA MP land surface model to then improve modeled SWE and stream flow. And so in this final part of my talk, I will explain some of the advances that have been made to this snow data assimilation by incorporating a dynamic observation error. So I talked a bit before about these two different ingredients that we need in data assimilation, but how are these ingredients mixed? How are the observations actually integrated into the physical model? And there's a number of different ways to do this. Here we use an ensemble common filter, or ENKF. So with the ensemble common filter, how strongly the model is corrected or updated by the observations is determined by the common gain matrix, which is very simplistically put here. And it depends on the standard deviation of the forecast error, or the uncertainty of the model forecast. And in the ensemble common filter, this forecast error is estimated by using an ensemble of model trajectories. And it also depends on the standard deviation of the observation error or the uncertainty of the observations. So the strength of the model updates is essentially determined by a statistical weighting of the model and the observation uncertainties. And if the uncertainty of the model is much larger than that of the observations, this common gain matrix approaches 1, and the model is strongly corrected towards the observational information. And if the model is much more certain, then this common gain matrix approaches 0, and the model is minimally corrected. So you can see how the treatment of these two sources of information, the forecast error and the observation error, is really important within this common gain matrix, and therefore impacts the effectiveness of the data assimilation system in general. And in most studies and at most observational centers, this observation error is assumed to be a constant static value that does not vary across space or time. And I think that this assumption may be okay for some observational information that's assimilated, such as LiDAR maps, for example. But is it a good assumption for satellite snow depth retrievals? So here on this slide, I now show the error of this machine learning snow depth product on the y-axis as a function of the retrieved snow depth on the x-axis. And so you can see that this error increases approximately linearly with the actual snow depth. And so given this figure, it's probably not optimal to assign the same observation error to an assimilated observation of 4 centimeters as you do to one of 4 meters, for example. And so here in this work, we compare two different data assimilation approaches. One that treats the observation error as a constant value, as is common in many snow DA studies and at most observational centers. And so here we assume this value to be 0.3 meters, which has been experimentally determined in previous work. And we refer to this as the DA const experiment. And the second experiment varies the observation error in space and time as a function of the assimilated snow depth. And so this is referred to as the DA var experiment. So here in this figure, you can see how this observation error on the y-axis changes as a function of the observation that's assimilated. yeah, you can see that with this DA VAR experiment, this observation air changes linearly with increasing snow depth. And importantly, we also set minimum and maximum boundary conditions on this air. So what I show here demonstrates the actual impact of incorporating this dynamic observation air at one example site. So if we focus on the left plot for a second, here I show an example time series at one specific site. The in situ observations that are used to validate the model are in black here. The open loop experiment, so this is without data assimilation, is in purple, and with data assimilation in red. And the green dots represent this machine learning snow depth product that is assimilated at this site. However, for this data assimilation instance, sorry, I'm moving the people around. Okay, sorry. For this specific instance, we have assumed this constant observation air. So you can see here that these air bars around the observations are much larger than this ensemble spread of the model. And so as a result, the data assimilation really minimally corrects the model at this site. And in contrast, on the right, when we vary the observation air based on the observed snow depth, the assimilated model result, which is shown here in yellow, is corrected much more strongly and as a result becomes more consistent with reality, which is this black line here. And then now below, I show an example site for a much deeper snowpack. On the right, this dynamic observation air towards the end of the season becomes much larger than the static one on the left. And so as a result, in this case, the model is not as strongly corrected here on the right, as you can see. And this varying observation air results in stronger model updates both earlier in the season and at lower elevations. So here I show a figure of the average increment. So this is the average change in the model from the data assimilation over the course of the snow season along the x-axis and at different elevation bands. And we can see that in general, the data assimilation is adding snow at higher elevations and removing snow at lower elevations. And that by implementing this dynamic observation air, we influence the strength of both of these updates. Okay, so this is maybe interesting and all, but does this actually improve things within the model? So on this slide, I show the impact on the modeled snow water equivalent. So in general, without the data assimilation, the model simulates too much snow in areas with low SWE and too little snow in areas with higher SWE. The DA const experiment here in the middle doesn't really effectively reduce this overall bias, and that's because of this relatively large observation air for these shallow assimilated snow depths. And so you can see here that a lot of this bias isn't effectively reduced in this experiment. And in contrast, the DA-VAR experiment here on the right is much more effective at reducing this bias because it leads to stronger corrections in these shallow snow areas. So here I show an example of the change in SWE between the DA-VAR experiment and the open loop averaged over the first week of March. So you can see that the data assimilation leads to pretty substantial SWE reduction in a lot of places, which is shown here in this red shading. And at most of the in situ measurement sites that were taken over this year, this leads to an improvement in the simulated SWE. And so that's indicated by these green dots here. Those are all the sites with improved SWE. And so here I show just an example at one of these measurement sites up here in Austria. The observed SWE is shown by the black dots, and it's much lower than the modeled SWE in the open loop, which is shown here in purple. We see that the data assimilation from the DA-VAR experiment here in yellow is much more effective again at correcting this and results in modeled SWE that is more realistic at this site. So I think with that, I will reach the conclusion of my presentation. I showed here today that combining Sentinel-1 observations with other information such as snow cover and elevation using machine learning can improve these Sentinel-1 based snow depth retrievals. And I also showed that incorporating these dynamic observation errors has a large impact on the snow data assimilation. And I think that this is an important thing to consider when designing future snow data assimilation experiments. Yeah, thank you.
Thank you, Devon. We will open the floor for questions now. We have about 7 minutes remaining. Niklas?
Yeah, thanks, Devon, for this great talk. This is really nice to see both the optical remote sensing and the active remote sensing in the same seminar. So I basically have two questions here which are related. The first one is, can you say a little bit more about the snow albedo assumptions the NOAA MP model makes for modeling SWE? And also, where do you see the potential of combining, let's say, Sentinel-1 snow depth estimation and also any kind of albedo products from instruments like EMIT or other hyperspectral sensors like Prisma or Nmap, which have like really good coverage of the Alps so far?
Yeah, that's a really good question. So to answer your first question, I don't know that I have a super great answer off the top of my head. I know that there are two different parameterizations for the albedo that we can use in NOAA MP. They're named class and bats, but I can't tell you much more information other than that. But it's, yeah, parameterized within the NOAA MP4 model. And
Yeah,
we
yeah,
did some experimentation with them and then chose the parameterization that worked the best for our study domain. Sorry.
yeah, no, yeah, because I'm also not too familiar with that model, and I was wondering if it's actually using data products from remote sensing instruments or if it's making some kind of artificial albedo decay assumptions or what exactly it does. But yeah, thanks again. And yeah, but the second question is maybe more related to your work. So where do you see the potential of like joining these different sensors and data products?
Yeah, I think that's a great question. I think there's huge potential, especially when utilizing a machine learning framework to kind of have these data fusion approaches. I think that's one of the huge benefits of machine learning. So, and that's something that we're kind of hoping to explore a bit more in our research group. So I know we have a master's student right now who's hoping to incorporate some additional information into this machine learning product, maybe some more optical information as well as some passive microwave information. And I think in the future with NISAR as well, that can be incorporated into products such as this. But yeah, I think with using machine learning, there's a lot of opportunity to improve like some of these data fusion methods.
All right, thank you.
Barira?
Can you hear me?
Hi, Devon.
Hello?
I can wait. I don't know.
Yeah, we can hear you.
Okay, cool. Great talk, Devin. I have a quick question regarding using constant error versus dynamic error. I'm just curious, in your work, did you encounter sites where you saw no clear pattern in observation errors, in like temporal or spatial pattern in observation errors? And if so, so did you find that using constant error on those sites were more beneficial than using dynamic error or vice versa?
Yeah, that's a good question. I looked at the air patterns generally across all of the sites. I didn't look at like individual sites specifically as much. There are certainly, as you see from maybe this figure here, some sites where the implementation of this dynamic air does deteriorate the results. And this is likely in places where the Sentinel-1 snow depth or the machine learning product is not super reliable. So we see that by incorporating this dynamic error, we often have stronger corrections towards the observations. And so if we're correcting stronger towards something that's like more inaccurate at potentially like these sites in red here, then we're going to have a deterioration in the results from this DIVAR experiment. It's possible that at some sites there we have more like constant errors in space and time, but I would be surprised if that happens at many sites. I think the pattern of increasing errors as the actual snow depth increases is pretty robust. Did that answer your question?
Yeah, thanks. Also, I can email you rest of my questions, but thank you so much.
Yeah, no problem. Thank you.
Yeah, we have a discussion going on in the chat right now. The original question was, what's the reason behind poor performance for Sentinel-1 observations in shallower snowpacks? And Ben said it's not sensitive to volume scattering, but I don't know if Devon, you had anything else to expand on that.
Yeah, I think there's been some recent field studies that show the sensitivity of Sentinel-1 is often at these layer interfaces within the snow. And so in shallow snowpacks, you maybe don't have as many of these layer interfaces. And so it's not very sensitive to snow below like 0.5 to 1 meters. I think its sweet spot is really like, yeah, maybe 0.5 to 3 meters of snow depth is where you can really get the most information out of it.
Can you suggest some improvement, like what kind of parameters we can incorporate to improve this sensitivity? Like since Sentinel-1 is having this issue, what other parameters we can incorporate in our model to improve this work, especially in mountainous regions?
Yeah, that's a good question. I think something that I incorporated into the model, which maybe was a bit skipped over because I didn't have much time to actually cover it, was snow cover fraction and particularly cumulative snow cover fraction. So in shallow snows, it's likely like snow that hasn't been around for a long time. So this cumulative snow cover fraction might be relatively lower. And I think while that's not like doesn't give you a direct answer of the snow depth, that incorporating that information into the model really did help, particularly for those lower snow depths. Yeah, that is maybe one example.
Another question regarding to this model only, like if let's say I am transferring this model from European Alps to some other places, maybe in US, maybe in Indian mountains, what are the things that I should take care of, or what are some additional improvements that I should make for that work?
Yeah, this is a good question. I mean, the short answer is that you really need data in the region that you want to transfer this model to in order to train the model for that specific region. So I've been working with someone recently in Morocco who was thinking to do something similar, but they only have 3 snow depth measurement sites in the Atlas Mountains. And so doing something like this there might be very challenging. And so I think with most machine learning studies, the problem of like enough training data is really a big issue. And so to bring this somewhere else, you really need to have sufficient training data available in order for something to be applied in a different region, I think.
Like let's say I want to train it on the same data that you have trained on, and then I want to use it in Indian Alps where I have few measurements just for validation. So will it work?
No, I don't think so. I think you'd have a tough time because the relationships between like elevation and snow depth will probably look very different in the mountains in India than they do in the European Alps. The mountains are much lower here. And so I think, yeah, your elevations there would be outside the scope of any of the training data that was used to train this model. And so I think, yeah, the model would really struggle with something like that.
I have one more question
Okay,
regarding to your. Oh, sorry.
we can continue this, but we just want to say we got to wrap up. We're past the hour. Thank you for all the questions too. I think if you could email Devon, she'd be glad to help answering these there, but we don't want to hold people past. Thank you all for coming. Thank you, Devon and Nicholas, for fantastic talks today. I think as Kate referenced, our next Center event will be at AGU. Is that correct, Kate?
Yeah, keep an eye out for that information, and we'll have one more seminar before the end of the year as well.
Awesome.
So yeah, to echo Jack, thank you so much. Yeah, we can be in touch if you need emails to follow up with questions. Please don't hesitate to reach out and forward the listserv information to your colleagues. Thank you so much.